folks. Sorry, my computer got stuck in the middle of an update. It's been taking 8 minutes so far to load up. But hopefully it's working now. Can you guys hear me? Awesome. Okay, what can I do for you this morning? What are you working on? I see a couple of you jumped into 8, which is into that chapter 8 test, which is great. I figured out why your chapter 7 scores weren't showing up. It was an old version of the test that was showing, not the new version. So you should be able to see those now. So yeah. So yeah, 2 or 3 of you did that chapter 8. Test so far. But yeah, what can I help you guys with today? You guys are like, nothing. You can help us with nothing. If that's the case, and you guys want to go play with that chapter 7 test, or sorry, that chapter 8 test or practice stuff, go ahead and do that. But other than that, you're going to have to let me know what you guys need today. If anything.
I just trying to see how to do the equation for polar. Like rewriting an equation for polar.
Given the Cartesian or?
Yes.
Okay. The nice thing about going from Cartesian is we have a nice direct substitution. Going the other way is a little bit harder. Let me grab a particular example here. Let me try to grab a particular example. So let's just say we use something fairly common. So say this y equals 3x squared. It's a nice parabola. It's a nice equation in Cartesian. But for whatever reason, we want to turn that into polar. Right now, there's not a lot of kind of motivation for why one might do this in polar, but you might be doing it in polar because you're using a particular set of graphic tools. But as you go along, particularly in Calc 3 and Calc 4, you'll get into scenarios where dealing with equations in the polar realm is much easier than dealing with equations in the Cartesian realm. So you'll have a problem that's stated in Cartesian, and it'll just be really difficult to work with, and somebody will come up with a good suggestion. Hey, what if we turn this all into polar? And you turn it all into polar, and you suddenly realize, oh, in this world, this problem is really easy to work through. So you work through it in that realm and then turn it back into Cartesian if you need to. So you kind of end up going back and forth with things. But as we recall, your definitions for sine and cosine, particularly, were our y values over our r values and our x values over our r values. That was our week 2 most general definition. So this actually naturally gives us a relationship between radial distances that we use in polar, x values, y values, and this angle. This angle x, y, and r are the same angle x, y, and r in polar as they were in our definitions. So that's where you get these, your polar substitutions that they mention, that r sine theta and the x equaling r cosine theta, that it kind of presents to you as, hey, this is the new rules for dealing with polar, but we really should look at those as something we've been doing for weeks, just in a different way. So if we want to go from Cartesian coordinates into polar, actually all we need to do is replace any x's with this r cosine theta and any y's with that r sine theta. So we end up with this, say, y as r sine theta, and that x as r cosine theta. Now, as soon as we do that, this tool is now in r's and thetas. So it's technically at this point in a polar form. The issue is that it's not in the polar form that we want, because we really, just like we like these functions solved for y, so they're functions of x, we'd kind of like to have this solved for r equals. Now, that's not always possible, just like it's not always possible in Cartesian to write everything as a function. But one of the reasons that polar can be very, very handy is a lot more things are functions in polar than they are in Cartesian. A great example is a circle. A circle in Cartesian coordinates isn't a function. But in polar coordinates, not only is it a function, but it's a very, very simple function. So, but we do still have to somehow solve this for r. But algebraically, we should be able to work that out. Sometimes they're harder than others. Well, that would end up being what, an r squared cosine squared theta. And we could say divide both sides by r. I don't want to divide both sides by r, do I? That assumes r isn't 0. And r could be 0 there. Okay, so I have all kinds of options. How about set this equal to 0? And we have 3r squared cosine squared theta minus r sine theta, if you want to do it that way. And then if we want to solve for r, we've got 0 equals r times 3 cosine squared theta minus times r sine theta. So r equals 0. How do they want that? Oh, they want that way. Okay. R equals 0 and r 3 cosine squared theta minus sine theta equals 0. And that's your 0 product principle. Either that equals 0 or this equals 0. We're going to focus over here. So here, your r times 3 cosine squared theta equals sine theta. I'm going to move that back over. And then just divide that stuff off. So r equals sine theta over 3 cosine squared. Okay. So it's a little bit of, moving things around a bit. And this is really, this is just a domain issue. If you want to divide off that r and have those cancel, and then just have this be r to the first, you'd get this same answer. But I like the, having the or r can be 0 is a nice case though, but that's gonna actually, that case is implied that r can be 0 when theta is what, pi/2. So you're gonna get that answer anyway. So that's me being really formal about those r's. So you could technically cancel them out in this case, but you can't always do that. So it's good to be careful of. So Beatrice, was it the substitutions or the solving?
I think it is the substitution.
Okay.
The thing, but also the solving as well, because I'm just like starting to. I read the book and everything, but I'm just starting to practice it, and the substitution and the solving as well. I'm having trouble with.
And part of that's just getting used to, again, like we did from chapter 7, getting used to kind of moving these things around. How we can play with this and how we can move them around. Because also you could kind of go, oh, well, sine over cosine. We know what sine over cosine is, right?
Yeah.
Sine over cosine is tangent theta, but then there'd be another cosine down here, and you could turn that into secant theta. So you could write the answer like that, and it's the same thing.
Okay.
If you wanted to. So it all kind of depends on how you move them around.
Yeah.
But this direction does tend to be the easier of the two, mostly because that direct substitution, anytime you see an x, you stick that thing. Anytime you see anytime you see an x, you put r cosine theta. Anytime you see a y, you put r sine theta, and then you solve in whatever way is necessary. Sometimes that solving is difficult. Sometimes that solving is not so difficult. It just depends on the structure you have.
Yeah. Can you show an example of like solving it, like the actual solving?
Well, that's actually what we were doing here, just solving for.
Oh, okay. All right. Okay, I think it's connecting now already. Yeah.
The harder direction is often the other one. If you're given things in polar, trying to convert them into Cartesian, like asking, what is this object 6 cosine theta? What is it in Cartesian? And we might again want that because it might be easier to work with in Cartesian, or we just might want it to be something we recognize more. And our conversions for going the other direction are the same conversions here, with the added knowledge that x squared plus y squared has to equal r squared. Well, that's always been true. The x squared plus y squared has to equal r squared, just says Pythagorean theorem holds, right? Yeah. So given those 3 relationships, turning something like r equals 6 cosine theta into turning that into Cartesian coordinates is often a little more difficult, because you can't just say, okay, any place there's a y, I'm going to put r sine theta. You can't just go, okay, anywhere there's an r, what am I going to put? Or anywhere there's a cosine theta, what am I going to put? You need to make, if you have a cosine theta, to do a substitution, you need an r times cosine theta. So you have to build that. If we have an r, if we have an r, we either need a sine theta or a cosine theta next to it, so we can put in an x or a y, or we need it to be squared, so we can replace it with an x squared plus y squared. Fair? So that it's often a more creative process, because we have to build the pieces for our substitutions, as opposed to anywhere you see an x, anywhere you see a y. Fair?
Yeah.
So one of the temptations here might be, well, if I square both sides, I'm going to get the r squared, and I could substitute the x squared plus y squared, and that would be great, except this other side is going to then be 36 cosine squared, and I still don't have an r over here. Fair? So usually focus more on getting the r's on your sines and cosines. So if instead of worrying about squaring the left, we just worry about, well, I need this right side to be multiplied by r instead of squaring. So I have an r cosine. Well, by our algebra rules, if I multiply this side by r, I have to multiply that side by r, right?
Yes.
Oh, look, I automatically built the r squared.
Oh.
Extra r's don't really cause as much trouble as lone trig functions. So as soon as we have that r cosine theta, we can replace that with x, because that's the definition. And our r squared, we could replace with x squared plus y squared. And we have an equation in Cartesian. Now, if we wanted to get fancier, we could say, hey, this is x squared minus 6x plus y squared equals 0. Just subtracting out 6x from both sides. And then if you remember your Algebra 2, Math 111 stuff, you can complete the square on this thing to make it a perfect square. You guys remember completing the square? Take half of that term and square it. Might have been a while. Got to add that same thing to both sides. So that's a perfect square. Factor it as such. I wouldn't be upset with you if you were like, oh, I kind of remember doing that, but it's a little fuzzy.
Yeah, I remember doing that, but yeah,
But fuzzy,
been a
fuzzy.
while. Yeah.
But then that means this is a circle. This is a standard form of a circle centered at 3, 0 with a radius of 3. So in Cartesian, we know what this object looks like. Well, that means if you switched your calculator over to polar mode and graphed r equals 6 cosine theta, you should get that same circle. And frankly, this 6, if it was anything else, half of that 6 tells you where the center is and what the radius of that circle is. So it essentially kind of turns us into pretty much a polar equation for circles along that x-axis. But what if you wanted the circle along that y-axis? Well, then it would be sine instead of cosine. What if you wanted it somewhere else? Well, then it gets more complicated. But not a lot more complicated, it just has cosines and sines. But the big takeaway is that for our purposes right now, going from polar to Cartesian will frankly usually be kind of like this. Usually will be things like circles, fairly nice objects, because we have to be creative in how we build our r sine thetas and r cosine thetas. Going the other direction is usually more straightforward because you just directly substitute, but the solving can be a little bit more hairy. So that's a real quick kind of generalization for switching from one coordinate system to the other. And again, it is one of those things that later, as it comes up, it turns out to be just super, 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 super handy. And as I said, one of the big examples is this is not a function. This is not y as a function of x. If you solve that for y, you're going to get plus or minuses in there, and it would just be a horrible thing to work with. But 6 cosine theta, that is a beautiful function. It's a easy to work with function. Once you learn calculus, that you think could almost not be easier to take the derivative of or integrate. That thing's just beautiful to work with. This thing's a pain to work with because all the square roots, when you try to solve, you have to break it into pieces so you make it a function. That's just a pain. Is that helpful?
Yes.
Cool.
Yes, that was. Thank you.
Mhm. What else you guys looking at out there? Oh, my computer is still locked up partially. It won't tell me what time it is. But what else can I help you with out there? What do you want to look at a harder version of that?
So I had problems going from the coordinates to the Cartesian coordinates to the equation.
Polar? Wait,
No, that part was easy. It was the equation going from the Cartesian coordinates to the equation, polar
Oh.
equation, or regular yes, polar equation.
So like that one we did first there.
Yeah, but with the coordinate system.
I'm not sure what you're meaning by but with the coordinate system. Oh, are you talking about like as a graph?
Yes.
Okay.
Yeah, I was doing that on the test yesterday and I ran out of time.
So do you mean kind of like these where you're looking at the?
Sort of, but you're taking it and I don't know how to say it. Let me move this bubble.
The roses are pretty. It does make pretty graphs though, doesn't it?
It does. I think, never mind, because I apparently don't know what I'm talking about and just need to go read my book again.
Well, that vocabulary is different once you get there. So, once you're dealing with polar, there is some kind of
She's in class.
talk in the talk that takes a little while.
Yeah.
Remember what number it was?
On the test, I think I missed 10, 11, and 12 because I just ran out of time and because I spent so much time on 10 on the test that I couldn't finish the rest of it.
Oh, yeah. Oh, so you were talking about coordinates then. Going just from Cartesian coordinates onto polar coordinates. Okay. So given Cartesian coordinates, say, I'm just going to use what you had, if you don't mind. They want you to turn that into r theta. Now, you've probably heard me say this before, but I think drawing that diagram out helps a lot. So xy would be back 5 and down 1. So our Cartesian coordinate, the -5, -1, right? And we're trying to replace that with an r theta. Well, that means we want to know this distance r and essentially that distance, that angle theta, right? Now, we know representations in polar are not unique, so we could use that r and that angle theta if we wanted to, or anything coterminal to it. Or if we wanted to get super tricky, we could use the negative r and use that angle. So use our theta facing into quadrant 1, and then use a negative r value to shoot us back into quadrant 3. So we got lots of choices. Fair? But what relationships do we know? We know that x squared plus y squared had better equal r squared, right? We know that r sine theta and r cosine theta, well, r cosine theta should be x and r sine theta should be y. But more to the point, we also know that the tangent of theta should equal y over x. And I'm particularly going to grab that one because we have x's and y's. Fair? So, well, let's just use those two tools. So if x squared plus y squared is supposed to equal r squared, then negative 5 squared plus negative 1 squared should be r squared. So 25 plus 1 should be r squared. So 26 is r squared. So r is equal to plus or minus the square root of 26. Fair? Now that plus or minus is important because if we use the positive root 26, then our angle has to point in this quadrant 3 direction, right? If we want to point into quadrant 1, we have to use the negative root square root 26. Fair? So we got to keep that plus or minus in mind. You can use either one, but you got to use the right angle with it. Fair? How do we find the angle? Well, we know the tangent of our angle is supposed to be negative 1 over negative 5, or the tangent of our angle is supposed to be 1/5. So if we take, what is in radians or in degrees? Radians, should do radians, okay. We should take that tan inverse of 1/5, right? But we know when we take the tan inverse, we don't get one angle, right? We get 2 answers per rotation and all the coterminals. So it's going to be that tan inverse of 1/5 plus any multiple of pi, right? Now, we know, without even figuring out what the tan inverse of 1/5 is, we know that the tan inverse of 1/5 is going to be this angle, because tan inverse can only give us answers in quadrants 1 and 4, right? It can't give us these quadrant 3 angles, so it's automatically going to give us this one. So whatever the tan inverse of 1/5 is, the tan inverse of 1/5 is going to be this little quadrant 1 angle. So if we wanted to use that tan inverse of 1/5, because we don't like remembering that there are other answers, we need to remember that there are other answers. But if we didn't want to use those, that's fine. We would just have to use the negative root 26 to have it shoot backwards. So going negative square root 26 at whatever the tan inverse of 1/5 is an r theta. And for my purposes, it actually asks you to enter exact value. To enter exact value, you have to put the tan inverse of 1/5. That's all you can put. Now, if you wanted to use a positive square root 26, you certainly can. But then you have to, instead of using that tan inverse of 1/5, we need to add that pi to it, right? So if you wanted to use that square root of 26 positive, you'd have to say, well, that tan inverse of 1/5, whatever that is, plus the pi, or subtract the pi and use that one, whichever one you know. So it's actually kind of nice in polar that we have these multiple representations. One of the reasons why so many things can be functions in polar that aren't functions in other systems is because points are not uniquely defined. You can't write them multiple different ways, like the point -5, -1. There's no way to write that point in Cartesian any other way. But in polar, we could write it in all these different ways. That's very helpful. It's very powerful, but it also means we have to make choices. And those choices come in those plus or minuses and in that extra angles. Cool.
Yeah, I got it now. No, I was just confused because I took so long on the test and then I started to freak out and I didn't remember how to do it. You know,
Yeah.
it happens. It boils down at the test.
And that's you know, that's not either unusual nor something to be, you know, overly worried about. That happens. What tool did you use for 10, by the way? Do you remember?
I have no clue. I don't remember anything. I just know I panicked. So I started just writing crap.
Okay. Because if you tried to do that with law of cosines, that could take a long time.
I actually think that might be what I did. I drew triangles. I think
Yeah.
that's exactly
Yeah.
what I did.
Yeah, and that you can do it that way, but it would take an inordinate amount of time to do it that way.
Oh, let me look really quick because I think I have my notes. If I can find the rest of them. Oh, here we go. I have my scratch paper. 8, 8. Yeah, it was law of cosines.
Yeah, it can work. It's just it's a nasty way to do it. If you look at either your notes or the video from Monday, we talked about doing that problem with the dot product.
Yeah.
And it's super quick that way. So.
I'm not allowed to use notes on the test.
Well, but if for future reference, you check.
I thought about it, but I didn't do it.
Beatrice, Kate, anything you guys want to look at? Or do you guys want to go play with that chapter 8 test?
I think I'm good.
Okay.
Yeah, I think I'm not good, but you know, I'm getting there.
But you're in a place. Yeah, you've still got to play with the
Yeah.
the 8-4 and 8-5 stuff.
Yeah, and I don't have no more of like the late, like the passes.
Oh, I can fix that.
Yeah, if you can, please.
Yeah.
Yeah, I just finished reading the book for 8.4 and 8.5. But I haven't still practiced it. But while I was looking at the book, at the examples that they give, that's something that got out to me.
Okay, yep, gave you late passes.
Okay.
Got a few more now.
Thank you.
Sure.
All right, then. Yeah, I just gotta practice it, do anything. If I have any questions, can I still like send them to you?
Yes, absolutely. And did you guys, did we talk about if you guys wanted to meet on Thursday before that final?
I think it would, for me, it would be good. Just
Okay.
is it gonna be like a review or?
It'll be whatever you guys need. So I'll just come and, like I usually do, say, what do you guys need? What do you guys want to look at? Which is,
Okay.
in some ways nice because then you guys can get answered exactly what you want, but it also puts
Mhm.
pressure on you guys to have prepared what you want. You know what I mean?
Yeah.
So
Yeah. Okay. Yeah, I would kind of appreciate for you to do the meeting on Thursday,
Yeah.
just to see real quick, because I am planning on taking the test, chapter 8 test and the final.
okay.
Yeah.
Then yeah, I'll be here.
All right, thank you.
Mhm.
Is that all? Is
That's
that for
all.
you today?
If that's all you guys need today.
I'm good.
Yeah,
I think
I'm
I'm
good.
going to roll over the review for the final.
Okay.
Yep.
Thank
All right,
you.
thank you. Have a good day.
You're very welcome. Kate, anything else you need?
No, I'm good.
Okay. Then you guys have a good day.
Thanks, you too.